All right, this is going to be the last video in this series on limits involving infinity, at least for now. Later, when we've studied derivatives, we'll return to this subject. However, the last thing I want to talk about is exponential and logarithmic functions. So first, as a review, here's the graph of e to the x, and here's the graph of the natural log of x. Let's talk about some of their limits. The graph of e to the x. If you look at the limit as x approaches negative infinity of e to the x, we have that this is equal to 0. You can see that going on right over here on the left side. Okay, so this is a horizontal asymptote here at x equals 0. It's a horizontal asymptote that occurs only on one side. Now on the other side, what's going on over here? The limit as x approaches positive infinity of e to the x is positive infinity. And this is one of the fastest growing functions that you can have. E to the x grows extremely fast. In the sciences, especially recently with the discussion of pandemics and the spread of disease, you'll hear people talk about things growing exponentially, and exponential growth is fast growth. Okay, so that's approaching infinity. Now, the natural logarithm is the inverse of that function. And so in particular, its domain is restricted. We can't look at the limit as x approaches negative infinity because the natural logarithm is undefined over here for negative numbers. However, we can look here. We can look at the limit as x approaches 0 from the right in particular, because again, the negative numbers would be not in the domain. So that limit is negative infinity. So this isn't a limit at infinity, but it is an infinite limit. Yeah, the vertical asymptote, right? So we have that one. And then the other end behavior would be over here. And this one is a bit deceptive, perhaps. It looks perhaps like there is a horizontal asymptote here, but there is not. If exponential functions are one of the fastest growing functions, a logarithm is one of the slowest growing functions. Makes sense, being inverses, right? So a logarithm grows very slowly. As it grows, its rate of growth decreases, but it does continue to grow. So the limit as x approaches infinity of a logarithm, in this case, the natural logarithm, still equals positive infinity. Okay. It just takes its time in getting there. Yeah, it just takes its time. All right. So with those reminders, let's do a couple of problems involving the exponential function in particular. We're going to look at the specific function e to the power -1 over x squared. We're going to use the same function for both of these examples. We're going to look at it in different places. In one case, we're going to look at x approaching 0. In the other case, we'll look at x approaching infinity. Okay. We don't really need to look at negative infinity because the behavior is going to be the same as this case. You'll notice that x is squared. So whether x is a positive infinity or negative infinity, it's not going to matter. Likewise, approaching 0 from the left or the right is not going to make a difference because, again, being squared, we'll get the same behavior on both sides. Okay. So how are we going to approach these? Well, these are both compositions of functions. As I have taught in class, a good way to approach composition of functions is with new substitution. In my opinion, I can't substitution. I have trouble writing and speaking at the same time. It's a term that doesn't just apply to an integration strategy, but rather to lots of different strategies for limits, derivatives, integration, solving equations, all sorts of things. So since we have a composition of functions here, I'm going to write it out. Y equals f of g of x. So y equals f of u, and u equals g of x. F of u is our outer function. That overall situation here is an exponential. E to the power u in particular is our outer function. G of x would be our inner function, the u, and that's what's going on inside there. It's -1 over x squared. I'm going to write it in the vertical fashion. So we'll start by examining this, the inner function. We'll start by examining the limit as x approaches 0 of -1 over x squared. we can solve this limit first by using the constant multiple rule, negative on the outside. Limit as x approaches 0 of 1 over x squared. Now, if you've watched my video on common functions, what is it? I call it the toolbox of functions, something like that. You'll know the graph of 1 over x squared. Okay, 1 over x squared is the graph that does that. Its limit as x approaches 0 is positive infinity, right? This would be positive infinity. But with the negative sign in front, it's going to be negative infinity. Okay, so what we've discovered here is as x approaches 0 from either side, u is going to approach negative infinity. So now we can rewrite this limit in terms of the u variable. This is a change of variable, folks. We're going to switch it to be the limit as u approaches negative infinity, the corresponding value that results from x approaching 0. And then in here, we can rewrite it in terms of u. It'll be e to the power u. So there, we've done the change of variables, and now we have a simpler limit to solve. That would be this, right? I know it says x over there, and it says u over here, but recall that the name of the variable doesn't matter as long as it's the same function. And the input's going to the same place, the output's going to go to the same place as well. So this is going to be 0. So that's the value of that limit. And that's an analytical solution for that. I know we did do some graphical reasoning here, but 1 over x squared is one of our basic essential functions that we basically memorize. Okay. Along with just like how this is one of the essential functions. Okay. All right. So, all right. So now let's look at the next one. Same function, x is going to infinity this time. Let's see what happens. We'll break it down the same way. We'll use u equals negative 1 over x squared. So we'll start by examining the limit as x approaches infinity this time of our u function, negative 1 over x squared. We can pull out the negative again. And sorry, now it's just positive 1 over x squared in here. And so now what happens here? As x approaches infinity, what does 1 over x squared do? Well, of course, if you've memorized the graph, this, we're talking about over here, right? It's going to be approaching 0. Just like how 1 over x approaches 0, so does 1 over x squared. And we were using that in the last video as well. This is going to be 0. If it's negative 0, that's still just the same as 0, right? Like that negative doesn't matter if we're multiplying it by 0. So, so that's where u is going as x approaches infinity, u is going to approach 0. And so now we can do that change of variables. We'll convert this to a limit as u approaches 0, and then write e to the u. And that, what is that? Well, the exponential function, go back up here to the graph, the exponential e to the x function, it's continuous everywhere in its domain. So in particular, when x equals 0, we would be looking at this point right here, 0, 1. E to the power 0 equals 1, right? So, so in this case, the limit of e to the u as u approaches 0. We can use direct substitution, and that's going to equal 1. There we go.